Hi, this is Miss G. These are notes on section 1D, method of initial rates, and what I'm going to do is show you how to calculate a rate law expression from rate data. So what you see here is 4 experiments were done in this for this chemical reaction that has 2 reactants. I'll call those A and B. And sometimes in these experiments the concentration of A was held constant and the concentration of B changed, and sometimes the concentration of B was held constant and the concentration of A changed, and the rate of the reaction was measured, and that's what you see over here on the right-hand side. The first thing I'm going to do is calculate the order with respect to A. So what you want to do is you want to find 2 experiments such that the concentration of A changed but B did not. So I'm going to pick specifically experiment number 1 and experiment number 3 because you'll notice the concentration of A changes but B stays at 0.1. So you write 2 expressions for both of those experiments. I'm going to take, because the rate for experiment number 3 is faster, what I'm going to do is write a rate law expression using experiment number 3. So I'm going to write 16.0 times 10 to the negative 5th. That's my rate. That's equal to some constant K. Don't know what that is. Times the concentration of A, which in this case is 0.2. taken to some power, or order, don't know what it is, so I'll call it M, times the concentration of B, which in this case is 0.1, excuse me, taken to some order, which I don't know. I'm going to divide that, remember this is experiment number 3, by experiment number 1, it's rate law. And so the values for that are 4.0 times 10 to the negative 5th is equal to K, times the concentration for experiment number 1 is 0.100 with respect to A, don't know the order, and for B the concentration is also 0.1. And you'll notice what happens here when we simplify this is we get 4 is equal to, K's cancel, concentration of B cancels, 0.2 divided by 0.1 taken to the mth power, which simplifies to 4 equals 2 to the mth power, and so m must equal 2. And so we'd say that this is second order with respect to A. So what I have on this slide is solving for the order with respect to B. And so what it is I picked 2 experiments. I picked experiment number 1 and experiment number 2 to work with. And the reason I chose those is because I need the concentration of A to stay the same, but I need B to change. Notice how it goes from 0.1 to 0.2. So I took the higher concentration of B, experiment number 2, and I wrote the rate expression for that. So I have the 4 times 10 to the negative 5th is equal to K times the concentration of A, that's the 0.1, taken to the mth order, times the 0.2 taken to the nth order, and I divided that by the rate expression for experiment number 1. And when you simplify this, 4 divided by 4 gives you 1, K cancels, see how conveniently these concentrations of A cancel, gives you 0.2 divided by 0.1, or 2 taken to the nth power. So n must equal 0. So this is 0th order with respect to B. In question number 3, you're asked to write the rate law for this reaction. That's simple because you have the orders. So you just write rate is equal to K times the concentration of A, and remember, we determined it was second order with respect to A, times the concentration of B taken to the 0th power. And it would also be correct if you wrote A is equal to K times the concentration of A squared, because we know that this really just goes to 1. So either of these would be fine. Question number 4 says, question number 3 says calculate the rate constant. So all I'm going to do is I'm going to take the data from experiment number 1. You can look at that on your paper from the data, and I'm just going to fill in numbers into that rate law expression. So from experiment 1, the rate is equal to 4 times 10 to the negative 5th and that's going to equal, sorry, that's a negative sign there, K times 0.100, and that's molar, squared. And the units over here were molar per second. And then you're just going to simplify, just solve for K. So when you do that, K is going to end up equaling 4 times 10 to the negative third, 1 over molar second. And that's your K value. Okay, so we now know what the orders are, and we now know what the rate constant is. So in question number 4, when it asks you to calculate the rate of the fourth reaction, you're just going to plug in your values. What we know now is rate is equal to K, which we just found to be 4 times 10 to the negative third, 1 over meters seconds, times the concentration of A, which is 0.050 molar, and we're going to square that because remember it's second order with respect to A, and then you're just going to multiply those two together. Don't forget to square, I don't know if you can see this, oops, don't forget to square the 0.05. Rate is going to equal to 1.0 times 10 to the negative fifth molar per second. The only other thing I wanted to mention is when you are working question 1 where you're looking for orders, every once in a while those don't come out to beautiful perfect whole numbers, so you want to get them to just round to the nearest whole number. That's fine. They're going to be close, but just get to the nearest whole number. So that's how you work these problems. What you're going to do is you're going to try the questions on page 18 and 19 and 20 and 21. It's just a lot of practice with this method of initial rates. So good luck.
Made with Doodlecast Pro.